Slept a lot the last couple nights. Alright, so today we're going to finish talking about engineered wetlands. And specifically, we're going to be talking about quantifying the hydraulics. We had these three kinds of wetlands last time, which were vertical flow, horizontal subsurface flow, and free surface wetlands. Which do you expect could accommodate the highest amount of flow?
Surface.
Why? Yep. That's true. It doesn't encounter any resistance from the porous media. If it gets too big, it changes the residence time, and so you're not going to get as much reaction that happens. So just because the water goes into a wetland and comes out the other side doesn't mean it's clean. It has to have the residence time to stay in the whatever it is, whether it's in the porous media in one of these horizontal subsurface flow or vertical flow, or has to stay detained in and around the vegetation in kind of a slow-moving environment in order for either the particles to settle out or some chemical reaction to happen. So yeah, free surface wetlands can accommodate more flow, but not hugely amount more flow, because the residence time is what matters. It's not just the volume, because if the volume goes way up, you're going to lose the residence, or if the flow goes way up, you're going to lose the residence time, and you won't have the treatment efficiency. We'll start talking about the hydraulics first in free water surface wetlands. But I guess first we have a few things to think about in terms of hydraulics in general. So one concept related to the hydraulics of any system, but of a... Can I somehow make this stop? We'll talk about the loading rate, or define the loading rate as Q is equal to the average flow over the area. So in this case, Q is the average, maybe annual or seasonal flow. And A is the not the cross-sectional area, but the overall surface area. Of a wetland. So this kind of looks like a Darcy velocity sort of a thing, but it's maybe more appropriate to think of it as like an overflow rate. Right? More like the Q that we used in the context of simple eutrophication phosphorus balances. Another hydraulic consideration is the residence time. And the residence time has to do with the volume. So tau, or the residence time, is equal to volume divided by flow multiplied by the porosity. So in this case, N is the porosity. volume is equal to area, surface area times the average depth. And the residence time is an important factor, because that's how reactions typically proceed in the direction we want them to over time, and so we need to just provide enough time. One other consideration here is that if, because of there can be instances where Q out does not equal Q in. When might that occur? You remember for wetlands what we talked about? What's that? Yeah. If there's some significant amount of evaporation, if there's some significant groundwater flow that comes in and dilutes it, or runoff from the adjacent land area, if Q out does not equal Q in, we can define the dilution ratio, or R, is equal to Q out over Q in. And then the effective residence time can be approximated as tau star is equal to tau times ln r over r minus 1, where in this case tau is the residence time based on the inflow rate. So the basic principle here is not one of, micromanaging residence times or trying to get the exact volumes figured out. It's much more big scale and sort of approximate than that. But the basic idea, because you have seasonally varying flow, you have evaporation, all kinds of different things. The basic idea is to estimate the physical size required for a given flow to provide a residence time sufficient for a treatment process to remove a contaminant. We know what the flow is. We have to figure out how big the thing needs to be given whether the hydraulic characteristics. For a free water surface wetland, we're still kind of in the realm of hydraulics here. Free water surface wetlands frequently have residence times of the neighborhood of 1 to 10 days, depending on what the treatment goals are. In order to avoid short-circuiting, it's recommended that length to width ratios be on the order of maybe 5 or 10 to 1, and the reason for this is so these, it should be 5 or 10 times as long as they are wide, and water depths, I should say design water depths, of somewhere in the range of 0.5 to 3 feet. If it gets a lot deeper than this, well, the right type of vegetation won't grow. And slopes are typically less than 0.5%. In order to quantify the flow in a free surface wetland, there's a couple different different regimes for very shallow slopes. That is less than 0.05%. Water depth can possibly be maintained with friction, gravity, balanced flow, and friction, gravity, balanced flow is sort of a Manning type situation. So there's various expressions that relate the water depth to the velocity using expressions similar to Manning's equation. A common one is that the velocity is equal to 1 over n times y to the 2/3 slope to the 1/2, and this is 1 for SI units. N can be adjusted for vegetation. And it's also a function of vegetation density and depth, but table 8.3 in the book has some information about this, but n can be written as proportional to alpha over y to the 0.5 power, where alpha is between 1 and 10 for y in meters. So anyway, there's a few other expressions, but if the slope is very, very shallow, it's possible that this kind of a flow could dominate. I have just an example of this to transition us into the other way that flow can be controlled in free surface wetlands. So in this example, there's a wetland cell is 800 meters long, 150 meters wide, and is on a slope of 0.0005. For densely vegetated system, that means alpha is equal to, just call it 10. So the question here is, what will be the residence time for a flow of 4,320 meters cubed per day, or this is roughly equivalent to 1 cubic foot per second. I think we get 0.05 meters cubed per second. So the first consideration would just be to find out if this what would be the residence time just if there was no control structure at all, and you can approximate the flow. Then Q is equal to V times A, or equal to 150 is the width times Y is the depth, times the velocity, which is 1 over n times y to the 2/3 s to the 1/2. In this case, n would be 10 over y to the 0.5, or the square root of y, and sparing the details, we could solve for knowing that Q is equal to 0.05 meters cubed per second. We can find that the water depth is equal to 0.069 meters. So what does that sound like? How deep is that? 7 centimeters? It's like 4 inches maybe, something. So that's fine. So we have 4 inch deep water. I mean, maybe that's fine. So the volume then is equal to the depth times the length times the width, is equal to roughly then in this case 8,000 meters cubed. Our initial flow rate was about 4,320 meter cubed per day, so without any control structure at all, the residence time tau would be equal to V over Q is 1.9 days. And depending on, I mean, perhaps this is long enough, but perhaps not. It depends on how rapidly the reaction rate is occurring within the wetland. What would be some options if you wanted to increase the residence time? Increase the length, so make a bigger wetland. If this is like one cell. Yeah, well, this was just based on a linear flow, and if you have flow going through an area, you have to make something bigger. If you're assuming a plug flow thing going through an area, it doesn't matter how twisty it is. You just have this amount of area that it's going through. You'd have to. So you could have additional cells, right? I said that this was just one cell. You could divide the flow in between 2 adjacent cells. That would effectively double the residence time if you had twice the volume. Or what else could you think of? Right. Put rougher sides in. More vegetation. I already maxed it out though. I already said alpha was 10, right? I mean, we're sort of running out of options here. And plus, this is, you kind of want to do this in an engineered system, and not such an engineered way. The hope would be to just have this kind of be a wetland that could run on its own. So we don't want to pull in a bunch of rocks to make the roughness different, or maybe you could change the slope, but that's gonna be hard. You have to have a lot of material to do that. Let's think about, what did I say the slope was? 0.0005 for 800 meters long. So what this looks like then is, if you think about it, it's 800 meters times 0.05. What was it? 0005? That's 0.4 meters, right? So over this 800 meters, it's dropped by only a foot or so over this. So it's pretty flat. Put a weir in, huh? How about that? If you put a weir in, now you can see it. So if you put a weir in, then that would increase the volume, which would therefore increase the residence time according to this here. And realistically, what was it? It was only 7 centimeters deep. You know, so it's going to drop by 0.4 meters over this whole depth, but it's only, you know, the water's only 7 centimeters deep throughout that. So if you put in a weir that was, I don't know, you don't want the water to be too deep downstream because you don't want it to be more than 2 or 3 feet. But if you put in a weir that was a foot or two deep, the water level would be, you know, a foot or two deep down here, and it would go back and be less deep or shallower farther up, depending on what the slope is. But okay, so a weir is a good option if we need a longer residence time. A weir can increase depth. For just considering a rectangular weir for the moment, if this is the length of a weir and the water surface is some distance above the weir, so this is sort of the solid weir, but the water is spilling over that. Call this H naught minus H weir, or delta H. Then the flow rate Q can be related to the weir coefficient times the length times delta H to the 3/2. Is something like about 2 or 1.8 for SI units. And L is the length of the weir. So for our flow of the previous design flow was 0.05 meters cubed per second, is equal to 1.8 times, if we do even a 1 meter wide weir opening, times delta H to the 3/2. It turns out that delta H in this case is less than 10 centimeters. So it's not going to change the depth that much. The big effect of this is going to be the fact that the water has to just pile up behind the weir and sort of flood the backwater area there. And if the weir width was wider, it would even be shallower depth, obviously. So now the volume is a function of the slope, weir height, and to some extent the flow, in as much as it leads to additional height behind the weir. Thinking this through a little bit farther, if we have some slope with a weir, and then some delta H on top of that, which is to some extent a function of Q. You can approximate the volume with some simple geometry. So the length, it's really the volume then is equal to the width of the wetland times the cross or the plan view area, and area can be approximated with two sort of rectangles here, depending on how far back or what's at the beginning of the wetland. But this is just an example here. Obviously, if the weir wasn't, what's the critical thing here? I guess this, whether or not HW plus H delta H is greater than the slope times the length will depend on whether it's simply 1/2 the area of the weir height times the length, or whether there's some standing water on top of the weir all the way to the back. So the other alternative would be, I have the expression written here, L times HW plus delta H minus slope times length. And actually there should be a, this is the rectangular part, and then this would be the triangular part. But regardless, the simplest way to do it is probably just to think about it in terms of average height. So volume is just equal to width times length times average height, without getting into the weeds. And of course, just a general design consideration is you can increase the residence to some extent by raising the weir height, but you don't want it to get too deep. Otherwise, it's not going to function as a wetland. It's just going to function like a lake, right? So the practical, H can be adjusted to achieve desired residence time. within practical limitations of a functional wetland depth. So what would happen if the slope was, if you had a higher slope, what would that mean in terms of the volume you were able to achieve with the weir, do you think? What's that?
Greater.
Well, you'd need a greater weir height to get the same amount of volume, right? Does that make sense? You could only build, if this slope up here was twice as much, but you could only have this max, kind of the max weir height is probably only 2 or 3 feet. So you're not going to be able to get near as big of a volume by building a weir if there's a significant slope. What would be the only alternative in that situation? It's not going to work very well because there's length to width requirements as well, but you could make it a lot wider, right? Imagine you just make the whole thing a lot wider, but then there's the idea that if you put the flow in on one side, it's only going to go right down the middle. It's not going to spread out along the whole thing. So that's why there's this idea of the length to width should be at least 5 or 10 to 1. So the bottom line is it doesn't work well on sloped surfaces. I think the book said 0.5%, but even 0.1% would be a fairly significant slope for a wetland. No natural wetland would ever exist on a slope that was 0.1% unless it was really, really clay, I suppose. All right, so then moving to the hydraulics of horizontal subsurface flow and vertical flow wetlands. Shifting here, we're not going to be thinking about Darcy's law and weirs when we're dealing with groundwater. About Manning's equation and weirs when we're dealing with groundwater, but it's going to be, everything here's going to be based on Darcy's law. So, so the slope in this case, there's a totally different paradigm here, in that previously we were talking about wanting to slow the water down in a free surface wetland. What do you think is the consideration in a groundwater system? Well, you want it to go at least, groundwater usually moves really, really slow, right? So in this case, you almost want to try to slow it down, or try to speed it up instead of trying to slow it down in a free surface wetland. So more significant slopes, I guess I'll say. You don't want the residence time to be years, otherwise the water's not going to move through. It'll pile up on the surface. More significant slopes needed. So more significant slopes are needed to provide the force for pushing the water through. In principle, Q, the total flow, is equal to area times minus K dH dL. And for a sufficiently conductive material, we'd like to have the design such that dH dl is approximately equal to the slope. So oftentimes slopes will be in the 1 to 5%. And conductivity in excess of 10 meters per day are typically necessary.